Have you ever stopped and wondered what really holds our world together? I mean, not in some big cosmic way, but right down at the level we can't even see. Well, today, we're going to dive into that invisible world. We're going to uncover the hidden forces and, believe it or not, the shapes that make everything possible. And our guide for this whole adventure? It's something you see every single day, a simple molecule of water. So let's start following the clues. And that right there, that's our first big clue. Because, and there's no other way to put it, water is just plain weird. It breaks pretty much all the rules you'd expect a molecule of its size to follow. So the big mystery we're setting out to solve in this explainer is this. What on earth gives water its strange, life-giving superpowers? I mean, just look at the evidence. For a molecule so small, it has a ridiculously high boiling point. It's got such high surface tension that it pulls itself into these perfect little droplets. And the weirdest one of all, its solid form, ice, is actually less dense than its liquid form. It floats. Now, these aren't just little quirks, you know? They are the very reasons life as we know it can exist. And the answer to all of them is hiding deep inside the molecule's invisible architecture. So to really get a handle on that architecture, we have to start with the basics, the atoms themselves. And it turns out there's a little competition going on between them. It all boils down to a constant, invisible tug-of-war over their electrons. This pulling power has a name. It's called electronegativity. You can kind of think of it like an atom's personality. Some atoms, like oxygen, are total electron bullies. They pull incredibly hard. Others are a lot more generous, way more willing to share. And this one simple property, believe it or not, it's the root cause of absolutely everything that follows. And here's where that tug-of-war really comes into play. So in a molecule like chlorine gas, you've got two identical chlorine atoms pulling on the electrons. It's a perfectly fair fight, right? So they share those electrons completely equally. We call that a non-polar bond. But then you get something like hydrogen chloride. The chlorine atom is way stronger, way more electronegative than the hydrogen. It just hogs the electrons, pulling them closer. This creates a slightly negative end by the chlorine and a slightly positive end by the hydrogen. And that's a polar bond. It has poles, just like a tiny magnet. Okay, so bonds can be polar. Big deal, right? Well, a single polar bond doesn't automatically make the whole molecule polar. The next piece of our puzzle is how these tiny little magnets are arranged in 3D space. And this, right here, is where shape becomes the absolute hero of our story. And the rule that decides the shape is actually wonderfully simple. Here it is. Electron pairs need their personal space. See, all the pairs of electrons in an atom's outer shell are negatively charged. And what do negative charges do? They repel each other. They're always trying to get as far away from each other as they possibly can. Now, chemists have a fancy name for this, VSEPR theory. But all you really need to remember is this little hierarchy of pushiness. See, those lone pairs, the electrons not tied up in a bond, they're the real bullies. They take up way more room and they push back much harder than the electrons that are stuck in a bond. They have the biggest say in what the molecule's final shape is going to be. Let's see how this works with let's call it a perfect molecule, methane. That's the main ingredient in natural gas. You've got a carbon atom in the middle, bonded to 4 hydrogen atoms. And the really critical thing here is there are no bossy lone pairs on that central carbon. So, with 4 identical bond pairs all pushing away from each other with equal force, they settle into this perfect 3D shape called a tetrahedron. And the angle between any 2 of those bonds is exactly 109.5 degrees. It's perfectly balanced, totally symmetrical. And this shows you just how important shape is. Because even though each individual carbon-hydrogen bond is a little bit polar, the perfect symmetry of that tetrahedral shape means all those little tugs and pulls cancel each other out. It's a perfect stalemate. The net effect is 0. So methane, as a whole molecule, is nonpolar. Okay, now let's bring it back to our main character, water. Water also has 4 pairs of electrons around its central oxygen atom. But here's the game-changing twist. Only 2 of them are bonded to hydrogens. The other 2 are those super pushy lone pairs. And remember how those lone pairs are the strongest bullies on the block? Well, look what they do to the shape. Instead of that perfect 109.5 degree angle we saw in methane, those 2 lone pairs just shove down on the bonding pairs, squishing them closer together. The result is a much smaller bond angle, only about 105 degrees. And this one change in shape, It changes everything. Because the molecule is bent and not symmetrical, those polar oxygen-hydrogen bonds don't cancel out anymore. Instead, they team up. They create an overall molecular magnet. You get a very negative side where the oxygen is, and a very positive side where the hydrogens are. And that, my friends, is it. That's the secret sauce. That's the source of all of water's superpowers. All right, we have all our clues now. We've got a molecule that is basically a tiny bent magnet. So the next logical question is, what happens when you throw a whole bunch of these little magnets into a glass? Well, they stick to each other. This sticky force has a special name. It's called a hydrogen bond. It's this unusually strong attraction that forms when the positive hydrogen end of one water molecule gets drawn to the negative oxygen end of another one. Now, it's not a full-on chemical bond, but it acts like molecular superglue, holding all the water molecules together with some serious strength. And hey, you don't have to take my word for it. Just look at the data. The power of this bond is screamingly obvious when you look at boiling points. To get water to boil, you have to pump in enough energy to get it to 100 degrees Celsius, just to break those hydrogen bonds. But look at hydrogen sulfide. It's heavier, but it doesn't have hydrogen bonds. It boils at -60 degrees. The difference is staggering, and it's all because of that powerful intermolecular glue. Okay, we've done it. We've followed the clues all the way from electronegativity to bond polarity, from molecular shape all the way to hydrogen bonds. And now, finally, we have everything we need to solve that original mystery. Why does ice float? As our source material puts it just perfectly, when water freezes, those hydrogen bonds don't just grab on randomly. No. They lock every single water molecule into a perfect, rigid, repeating position. They build a highly organized crystal. So here's the bottom line, the crucial difference. In ice, all the molecules are held at arm's length by those stiff hydrogen bonds, forming this open, cage-like structure with tons of empty space. But in liquid water, those bonds are constantly breaking and reforming, allowing the molecules to tumble around and pack in much, much closer together. The disorganized liquid is actually denser than the organized solid, and that is why ice floats. So there you have it. From a simple tug-of-war over electrons to a bent shape, which creates a polar molecule, which leads to super strong hydrogen bonds, which results in floating ice and, well, life on Earth. This invisible architecture is absolutely everywhere. The next time you see oil and water refusing to mix, or you catch a snowflake on your glove, you'll know the secret is all in the shape. So what other everyday mysteries do you think are waiting to be explained by these exact same rules?